Bismillahirrahmanirrahim. Assalamu alaikum. Yes, hello everyone. How's it going? Hope that you are getting through the knowledge of fires and explosions and getting a sense of how do fires occur into being happening in an industry or happening at home. So what we have taken from last time was 6.1 from chapter 6, and that was about fires and explosions. We were just taking some kind of an introductory to fires and explosions and about the fire triangle. So the first thing we have taken 6.1 was the fire triangle, in which you need the fuel, the oxygen, and the source of ignition. And then in 6.2 from Kroll's book, Chemical Process Safety, we have taken the difference between fires and explosions. And in 6.3, we have taken this flammability limit. So before I enter 6.4, so I just want to remind that what we have in this picture here. So in this figure, we just wanted to know, it's like it collects all the definitions. We have taken many definitions for flammability limits. So what I need to understand from this figure, well, it needs to be in the gas phase. So this is mist and this whole region's gas. So I'm saying that in the gas phase, it will be reacting with oxygen, which means combustion. So this is the combustion stage. And this combustion stage, if the volume, if the concentration increases within a certain limit, that means beyond that limit, it will be not flammable, right? And that is the upper flammability limit. And beyond a certain limit, if the concentration was too low, the volume percent was too low, then that means it will also be not flammable. So the flammability region is this region here. Okay, is that region here. And that region, it will be flammable with some ignition of source. However, if you exceed an auto-ignition temperature, which is a temperature, if you exceed a certain temperature, it will auto-ignite by itself. Great. And now if you go lower, here is all gas, right? So what separates liquid and gas? What separates liquid and gas? What separates liquid and gas is the saturation vapor pressure, which is also a function of what? A function of temperature. So this is a function of temperature, right? This is a function of temperature. And because it's a function of temperature means that curve could be changing from one, of course, from one component to another, but also at different temperature, it may give me a different curve. So what else do we have in this figure? We also have the flashpoint, which is the point where we have our first flash, first fire. Okay, but it does not propagate, so we don't call it a fire point. So fire point could be somewhere here, for example, where then it is going to be propagating, okay? And definitely it will not be lower than the lower flammability limit, and of course the flash point will be at the lower flammability limit here. Okay, so these are the things that we have taken from last time, and it's good to see the differences. And it's very important to know, like, this flash point and flammability limits, the ones that we are finding, they are not fundamental properties, okay? It's not like density, viscosity, they are not fundamental properties, but all of them, they are specified through experimental apparatus. So all of these limits that we can see here is all found through some kind of experimental experiments. It's done through experiments. Great. So now we're ready for 6.4. So now we know all the definitions about flammability, UFL and LFL. Can we work more now about it? Yes. Flammability characteristics. So we can know those characteristics of the flammability of liquids and gases because everything is there is in Appendix B. Appendix B. So where is Appendix B? So if you go So if you go to your book at page 646, you're going to see here Appendix B, flammability data for selected hydrocarbons. And for example, if I want to talk about methane, so here I have methane, and this methane, the lower heat of combustion, which is the lowest energy that we have that comes out. Well, let me go to the flammability limit. The flammability limit for volume percent fuel and air, the LFL for methane is 5. The UFL, upper flammability limit for methane, is 15. What is the flash point? Flash point is 1 minus 188. So you can see how low is that flash point, and just gives you an indication that methane is ready for any fire. It's just a very small ignition of source because it's already within a room temperature, right? So it's much above than that, which means if you want to store methane, I think so it will kill you and you will not be able to do that. So what is the auto ignition temperature? Now, so on the other side, the auto ignition temperature is 600. That means if you heat it to a certain limit of 600, now it will auto ignite by itself and it will catch fire, even without a source of ignition. Okay, that heat is enough as an energy to do the process of getting ignited, and the process of the reaction happens for oxidation. Great. So this is what we have here for the flammability characteristics. So let's continue on. Flammability characteristics, you can find that in Appendix B. So the flashpoint temperature, we already can see it in Appendix B. Now, for some, we already said that the flashpoint temperatures, we can get it using the open cup method or the closed cup method. So if just to get an idea, we already have taken this very briefly. But what is the Bunsen burger that is we can use to find out the flashpoint temperature? So if you have, for example, here, this is like the open cup thing. And what you can see here is that you have a gas supply. And as you have the gas supply, you have a test flame, which is a very small flame. You're increasing the temperature and making sure that when you're going to have your first ignition. And this is the thermometer, in which you're just every time checking what is the temperature in which you get this flame. Okay, so you're heating up with the heat plate. Okay, so this is like the heat plate. It's heating up what? Heating up my cup. Okay, if you just can see the cup. So where's my cup? This is my cup here. Okay, that is my cup here. So that is my cup, open cup. And what do you have here? You have heating plate, and of course you're going to have vapors of that of this what is in the cup here, and the time that you just have this flame is it just tells you that this is the temperature, the flash point in which we are going to identify. And you can see that this is mainly experimental, so it's not a fundamental property. It changes with many different conditions, and it's very difficult to fix all those conditions. So we just get it experimentally. Okay, great. So if I would say, like, is there an easy method for calculations? Someone did the experiments for us to identify the flashing point for many different materials. Yes, there was Satyana Rayana, oh my god, and Rao showed that the flash point for pure materials correlate with the boiling point. So there is a relationship between the flash point and the boiling point, and they have done this for 1,200 compounds. Okay, so they helped us, and they told us that this has an error of about 1% using this equation. So this equation tells me that TF, which is the flash point, is a function of A, B, C, and the boiling point. We can get the boiling point from properties of materials. That's easy. So we need only ABC. Where to get ABC? You get them here. You see, ABC for these hydrocarbons, any hydrocarbon, methane, propane, butane, pentane, and so on. And all the rest, which is alcohols, amino acids, ethers, for all of these are the values that you have for A, B, and C. And you just substitute to get what? To get the TF, okay? To get the TF, the flashing temperature. And one important thing that I already mentioned is that the vapor pressure, of course, is going to be changing with temperature. And it just increases with the increase in temperature. I just wanted to mention that because it's important. And one more thing that you need to know, that between the lower limit and flammability, upper flammability limit, you're going to have your combustion. You're going to have your flame, right? Below that, no combustion. Over that, no flames at all, right? So it's only between these two limits. However, the thing that you want to mention here, that between these two limits, it is not always you're getting the same energy, okay? The same pressure. You're getting different pressures, okay? The amount of energy that is that is coming out of that reaction, it is different. So we can see that about 10% volume percent of methane in air, we are getting our maximum value. And of course, this will be different for different volumes or for different materials and so on. Great. So that was about gases in 6.4. Now talking about the, that was about liquids for 6.4 and talking about the flashing point. Now we want to talk about the gases and vapors. So gases and vapors, of course, they also have flammability limits, are determined experimentally, however, in a design closed vessel apparatus. Vapor-air mixtures of known concentration are added and then ignited. Okay, so this is what we do. We try to ignite our vapor air mixture that we have. So for example, we have methane air mixture, okay, and we want to know when does that ignite exactly. And then we also know that if it ignites, it's already in gas, we may have this maximum explosion pressure, and we want to know what is the maximum explosion pressure. And the test is repeated with different concentrations to establish the range of flammability, to know the lower flammability limit and the upper flammability limit. So for methane, for example, let's see a general example, sorry. So this is the equation. So frequently, let me read that. Frequently, LFLs, UFLs for mixtures are needed. These mixtures limits are computed using the LFL equation. So that is the equation that we have for LFL and UFL. So simply, it tells me that I have a mole fraction. It's very similar to what we have taken for the threshold limit value, okay? It's very similar. And then you can know that if it is flammability mixing by getting the LFL mix, and then by adding all the LFLs and seeing, it's not adding the LFLs, adding the concentrations that we have, the percentage, the volume percentages that we have. Okay. So what do we have here? We have the LFL mix and we have the UFL mix. What is YI? YI is the mole fraction on a combustible basis. And what does on a combustible basis mean? It means that you are considering only the combustible gases without the rest, And what do I mean by without the rest? So only the flammable materials are only considered to get the mole fraction. And when we solve, you will understand what I mean by that. So it's not the total. What is LFL? It's the lower flammability limit, and it's represented in volume percentage. YI is the mole fraction on a combustible basis, and N is the number of combustible species. N is the number of combustible species. So that is very, very clear. That's the number of moles. Okay, so what do we have here? Sorry, it's not the number of moles, it's the number of the species. So if I have two species, methane and whatever, butane, okay, so I will have like two species here. So y1 over LFL1 plus y2 over LFL2. Okay, now that flammability is really calculated at 25 degrees, usually because all our properties are provided at 25 normal operating conditions, or I mean the normal room conditions. So if I want to calculate LFL at a different temperature, this is the equation that I'm going to use, and you can see that this equation is like just an equation of assuming like a linear relationship, and what I'm doing here is like just an interpolation. Okay, so what is the equation? It's LFL 25 at 25 degrees, right, minus 0.75 over the delta heat of combustion at 25 degrees, which we already can get that from Appendix B. And in the case that we have more than one component, we are going to calculate the net heat of combustion. And then you multiply at the temperature that you want to find the LFL at that temperature, minus 25, which is the original temperature. Okay, so these are the two equations for LFL. So these are the equations to find for the mix. And then if you want to find a different temperature, you're going to use this equation. And if you want to find at different pressures, okay, at different pressures, then you're going to use this equation here. And you can see that there's only one equation that we have for UFL, for UFL only. What about LFL? Okay, what about LFL? Where is it? So what I said here at the beginning, pressure has little effect on LFL, except at very low pressures, where flames do not propagate. So what we are trying to say here, that LFL does not change with pressure. Okay, LFL does not change with pressure. So here we say that we just assume that our LFL does not change with pressure. However, talking about the UFL increases significantly as the pressure is increased, and this is how we can see. Of course, when we say that UFL increases significantly, what does that mean? That means the flammability region became bigger, right? So instead of having a flammability region, if you can remember, this was like my curve, the the pressure vapor curve, and here we had mist, and here we have like lower flammability limit and the upper flammability limit and the auto ignition region here. So what we are showing here, we are saying that, oh my god, okay, instead of having this region here, this upper flammability limit is going to be higher, that means somewhere here, and the lower flammability limit is not going to change with pressure. So now instead of having only this region, I'm having a bigger region of flammability, okay, a bigger region of flammability. So that is the effect of pressure. It just makes it much wider for a flammability region. Okay, great. So now how can we calculate the LFL? Okay, how can we calculate the LFL? It's not always easy that we can calculate the LFL, but let us see how to do that. And let me correct this. This is the stoichiometric concentration. Okay, for some situations, it may be necessary to estimate the flammability limits without experimental data. So usually you find them through experimental data, and we already have seen that you can do this. You already have flammability data for selected hydrocarbons, where we have the LFL. You have the LFL, you can see in the middle here. You have the LFL and you have the UHL. Let me see if I can highlight this thing here. So you have the LFL and you have the UHL, okay? So you already have these two values here. And you have them for what? You have for many hydrocarbons. They are selected ones, of course, and you can see here. And you also have for terpenes, alcohols, aldehydes, ethers, ketones, acids, esters, and so on. So you can see that you have a lot. You have a lot that had already been done for us. So what we are talking about here, we are saying that sometimes we need to do our own calculations as well. okay, as well. So there have been many attempts, and good attempts I would say, to calculate the lower flammability limit. So the first method that we want to see here of how to identify the flammability limits is that LFL is equal to 0.455 into the stoichiometric concentration. You call it the stoichiometric concentration. And of course, the first question comes here, what is a stoichiometric concentration? Or how can we really find that? So Jones found that for many hydrocarbons vapors, for the LFL and the EFL, they can be a function of the stoichiometric concentration as follows. And what is the CST? It is the volume percentage of fuel and fuel plus air. Did you get that? So it's the percentage of fuel divided by fuel plus air. And to make it easy, actually it seems easy, but let's see a general equation in which if I have something that looks like that, so this is like a generic hydrocarbon thing that we have, or whatever, a compound that we have, which it has CH and O. Of course, for hydrocarbons, we don't have O, so Y is always 0, right? Y is always 0. So if you have CmHXOY plus ZO2, giving me a CO2 and H2O for full combustion, and if you have this system here, it follows that for a stoichiometry, this Z is always going to be M plus X over 4 minus Y over 2, okay? If you just want to do it by your hand if you want, but this is a generic equation that fits all reactions, okay? For all reactions, it will always be that. Great. So what do we have here? We have Z is equal to M plus X over 4 minus Y over 2. So I can find what is Z. So if you go back, so if I want to find CST, which is a function of Z, so what was the CST? If you can recall, that it is the function of, it is the volume percentage fuel in fuel plus air. It is the percentage of fuel in fuel plus air. So let's go and see it back. Okay, so what do I have here? Z has the units of moles of O2 divided by mole of fuel. And CST as a function of Z here, which is that stoichiometric ratio here, it is equal to CST is the moles of fuel plus moles of fuel plus moles of air multiplied by 100. Just rearranging it, and we know that oxygen is 0.21 of that air, right? So it's 0.21 of that air. Rearranging, doing our calculation. Oh my god, it didn't show me the equation. Okay, so that was the equation, 100 plus over 1 plus Z over 0.21. Of course, that was the case that we have air, and this is the equation that we have obtained here. Actually, there are simpler equations, and we're going to see that in a moment. Let's take an example. So if the UFL, this is an example actually for pressure. I should have given an example for something else, but I would say I'm sure that I have included examples already. So if the UFL for a substance is 11% at 0 megapascal gauge, what is the UFL at 6.2 megapascal gauge? So that is straightforward, I would guess, right? So what do I have? The absolute pressure, of course, we need the absolute pressure, which is 6.301. The UFL is determined by this equation. So you're simply substituting UFL at a certain pressure, which I want to know now what is UFL at 6.2, which is, 6.301, is equal to UFL plus 20.6 into log P plus 1. So log 6.301 is the new pressure that I want to find, into 20.6, that is part of the equation, plus 11. So where did he get the 11 thing? Okay, where did he get the 11 thing here? It's already given to us. If the UFL for a substance is 11%. I was going to take you to Appendix B. I thought that they gave us here the name of the material, but we don't need to do that because it's given to us. And remember that it's always percentage by volume, okay? Percentage by volume. I think this is straightforward, and it just tells us now the UFL is 48% of fuel in air, okay? The upper higher limit. It increased. So now considering what we have taken, and are there other ways finding the lower flammability limit and the upper flammability limit? Are there other ways? Yes, there are other ways. And you can see this is another way in which you can calculate the lower flammability limit and the upper flammability limit. And actually you also can find a way in which you can find the lower flammability limit based on the heat of combustion, and the upper flammability limit based on the heat of combustion. So you can see like there are different ways. We found that we can find it through the CST, right? Or you can find it directly here using the XYM thing, okay? Or we can, like this is like one, this is like another method, okay? That was from the top there. And now we are using the delta heat of combustion. So these like are different ways of how to calculate the LFL and the UFL. So let's see an example now, just to get that grasped by our mind. Estimate the LFL and UFL for hexane and compare the calculated limits to the actual values determined experimentally. The stoichiometry is that. So this is the equation that we have, right? And what are the values? It's already gave me the values. M is equal to 6. Actually, sometimes they don't give us the values. We need to balance the equation. And when we balance the equations, we are going to find these values here. So for this case, we have M is equal to 6, X is equal to 14, Y is 0 because there's no Y, there's no oxygen here, right? So let's calculate. So LFL, you're going to use the equation 610 and 611. Oh, so what is 610 and 611? You can see it here, okay? 0.55 into 100, that's 610, huh? Divided by 4.76 m plus 1.19x minus, that is 0, minus 2.38 into y plus 1. So what do we have here? 0.55 into 100 or 4.76 into m plus 1.19 into x plus, of course, there's minus something 0 plus 1. Okay, so you're going to calculate the LFL. If you calculate the LFL, you're going to find it as 1.19 volume percent. Compare this C6H14, which is hexane. Okay, and let's just go to appendix B and see what is the value. Okay, the value for hexane C6H14, it is 1.2. LFL is 1.2, so that is 1.2. And the UFL is 7.5. Okay. So what do we have here? We can see that our LFL, which is 1.2 from the tables, which is done experimentally, our way of calculating it was very accurate. It was 1.19. And you can see that our UFL, which is done by hand, it was 7.57. Experimentally, it was 7.5. That is a very good indication. And again, doing it by hand, it helps for faster calculations, because it's not always easy to do your kind of experiment to find out the limits. Okay, great. So this is about the flammability limits in air, right? We're talking about air. What about the flammability limits in pure oxygen? Well, in pure oxygen, things are going to be different. Why? Because you're talking about the pure oxygen. That is not a 0.21% of that air is oxygen. We are talking about pure oxygen, right? And for that, we have something different that we will state here, which is like talking about the lower oxygen limit and the upper oxygen limit, okay? So now these are two different parameters as well. But of course, I always go back say that these are very important because we need to know how much oxygen is available. But even the lower flammability limits and upper flammability limits are very much used because we are always dealing with air. So we need both of them, if I would say. But mainly you will use the LFL and the UFL. Okay, so just to know that how to do my calculation, the LOL is not laughing out loudly. Okay, it's not LOL. Okay, so if the LOL, the lower oxygen limit, it is equal to the LFL. So we just make a very easy definition there. They are equal to each other. Okay, so LOL is equal to LFL. Okay, so it's approximately that. What about the UOL? Very similar to the pressure, where you said that the UFL changes with pressure. The UOL also changes, and it is a function of that equation here. We know UFL, CUOL, it is a fitting constant, and somehow Hansen and Kroll found a good fit for a number of fuels, and this good fit just keeps one constant for most of them, which is minus 1.87. So you always can use minus 1.87 for CUOL. So now you have UFL, you have the concentration UOL, and you have UFL, you have CUOL. What you don't have here is UFL not, okay, UFL not, or UFL oxygen. So what is UFL oxygen? Is the oxygen concentration, okay, the oxygen concentration at the upper flammability limit. So simply, what is UFL oxygen? It is the volume of the oxygen in air, volume percentage of oxygen in air. Okay, so let's take an example, and that will clarify things up. So estimate the UOL for methane using equation 614. And equation 614, the one that I just presented here. So from appendix B, we can find that UFL is 15 volume percentage. So UFL is 15%, just to make sure. So what is methane? Here's methane. What is the UFL? It is 15. Okay. So UFL is 15%. If we select a basis of 100, so just say that we have a basis of 100 moles. So if we say 100 moles, that means how much do I have of methane? I have 15 methane and 85 of air. Okay, so that's what it means. Again, 15 methane, 85 air. And that is why my UFL, the upper flammability limit for methane here was 15 moles divided by 15 plus 85, which is 100. So how much air do I have? 85. How much oxygen do I have? 0.21 multiplied by 85 of that air, I get 17.85. So that is my UFL oxygen. So I have my UFL of methane, I have my UFL of oxygen, which is UFL naught. So I'm going to substitute UFL oxygen, and I'm going to substitute my UFL of 15%, and I only have the CUOL, which is minus 1.87, and then voila, I'm getting my percentage, which is 62.4%. If you compare this experimental value to table 6.3, okay, you'll find that it shows that it is 61%, which means that I got a very good approximation here. If you want just to look at 6.3, what is table 6.3? That is table 6.3, table 6.3, methane. Okay, let's go here. So this is where you can have, like, let me see here, CO2 with air and 2 CO2. Do I have methane? Just let me check here for a moment. Okay, yes, that's what we have. We have methane, and we want to see the UFL. We need to see the UOL. Okay, where did this take me back? Just a second. So yes, so as we said that this is 62.4%, I thought that the value of this value is shown in the table 6.3. Actually, it's not shown because table 6.3 only shows the limiting oxygen concentration, which is the LOC. It does not show the higher one. Okay, so that is the way of how to calculate the UFL and the UOL. So let's take another example. Estimate the LOC for butane. So how do we calculate LOC for butane? So as you can see that we have a reaction for butane C4H10. Of course, we have no O here. And we have written our reaction here, C4H10 plus 6.5 O2, giving us 4CO2 plus 5H2O. So, of course, this is written for you, but you need to balance the equation by yourself, okay? You need to balance the equation. Of course, you're going to find this anywhere in Google, right? But I say, that's simple. That's just a piece of cake. So the LFL for butane you find from Appendix B is 1.8% by volume, and then you can find the LOC. And as we said that LOC, the only difference from LFL with LOC, we are going to take very similarly that LFL is equal to LOC, except that we are going to consider that how much oxygen do I have, okay? How much oxygen? And in this case, I have 1 butane and 6.5 oxygen, okay? 1 butane and 6.5 oxygen. So if you multiply 1.8%, the one that I have, with 6.5 oxygen, you're going to have 11.7 volume percentage O2. And that is my LOC. That is my LOC. So the combustion of butane is preventable by adding nitrogen, carbon dioxide, or even water vapor until the oxygen concentration is below 11.7%. Okay, so I just want to make this clear again. For example, I'm adding nitrogen. Why I'm adding nitrogen to butane? To keep the oxygen lower limit, the limiting oxygen concentration, which is 11.7%. I want to go lower than that so that I make sure that I don't get into that region. I don't get into that region that it could be flammable. Okay, so the addition of water, of course, is not recommended because water has oxygen by itself, right? Because any condition that condenses water would move the oxygen concentration back into the flammability region. So we need to, of course, be careful which inert, right? Which inert, and inert, that means anything that you're adding to the system and does not react. But in this case, it's like we have water vapor could react and get oxygen within the system and making it flammable. It's not reacting, but it's adding to the system what could make it flammable. Okay, so example 6.6 shows that the LOC can be estimated using the equation LOC is equal to Z into LFL, okay? Z into LFL. So what we have done, we have taken Z. I know that you didn't think of it as Z, but this is what we have done here. That was Z. Z is simply saying that this is 6.15 divided by 1, okay? This divided by that. So that was like a simple, straightforward. Okay, great. So Hansen and Kroll found that a better estimate of the LOC is given by, so these guys, and we know Kroll, who's one of the authors of this book. So he said that they can find the LOC using this equation here. And just to make it maybe simpler for the calculations. And however, for LOC, now we have a new constant for CLOC, which is equal to minus 1.11. So we had it minus 1.87 earlier. Here it's minus 1.11. Again, if you want to take just an example, this example says that please estimate using equation 616, compare the results of 6.6. From Appendix B for butane, LFL is 1.8%. And just to be sure, let's go to butane. So here's butane, where's LFL? Here's LFL for butane. Okay, so it's 1.8. So that's 1.8%. What is UFL? UFL is 8.5%. The equation is, the problem is asking me to find what? LOC. How to find LOC? I need this problem. I have LFL 1.8%. I have CLOC, which is minus 1.11. I have UFL, which is 8.5%. So the only thing that I don't have here is this thing here, which is UFL oxygen, UFL not. And so UFL oxygen is equal to the amount of oxygen, which is 0.21 in air, Okay, why? Because all these problems here are within air. Okay, so the LFL is within air and UFL is within air. So to consider how to calculate UFL for oxygen, we multiply 0.21 into 100 minus 8.5, and that will give me 19.21% oxygen. So why did I subtract 8.5? I'm just saying that if I take the maximum of butane that I have, which is 8.5, and remove that, the rest is what? The rest is air. So 100 minus 8.5 of butane is air, and if you multiply by 0.21, you're going to get the oxygen. Okay, so you're going to calculate LOC, and LOC is going to be 12%. If you just compare that to the experimental value, that is in table 6.3, it shows you that it is 11.7%, which is lower than the experimental value. Okay, lower. And as you can see, that is very close. These values are very close, and you can see how accurate was that equation to help us there. Great. So this is what we have for 6.4. I hope that you have learned from what we have taken today, and what we are going to take in the rest of our lecture. We are going to talk about the flammability diagram, and of course we are going to talk about explosions later. So we are going to talk now about the flammability diagram, and then we're going to enter to explosions. The flammability diagram, of course you already remember the triangle. However, now we are going to look at the triangle by a different way, because we are going to use this triangle as a calculation. Okay, it's going to be used for calculations, and I know that sometimes sounds a little strange for you how to use a triangle in some calculations. We are going to see that in our coming video. So thank you very much. I appreciate your presence here, and I hope that you have gained from what we have taken so far, how to find the different characteristics. So what we have taken today is the different flammability characteristics, and flammability diagram is one of those flammability characteristics, which we are going to take in our next video. Thank you very much. I appreciate your presence here, and see you in the next video. Ma as-salama.